afternoon or good morning, everyone. Welcome to the seminar series on the resilience of autonomous systems. Today's speaker is Mario Gleirscher, who is a postdoctoral researcher and a lecturer at the University of Bremen in Germany. Mario received his PhD and Master of Science degrees in computer science with a minor in mathematics from the Technical University of Munich. And he has a foundation degree in mechanical engineering, having collected multiple years of practical experience as a consultant, method engineer, and software developer. His research and teaching interests are in verifiability of correct control of intelligent cyber-physical systems. And for his research, he was awarded a fellowship at the University of York, funded by the German Research Foundation. So he is a close collaborator of our team and research group. Mario, the floor is yours.
Thank you very much, Radu, for this kind initiation. And yeah, thanks everyone for joining, also for inviting me to this seminar series. I'll today talk a little bit about research that began in more or less when I did my PhD, but it has gotten more tangible actually when I moved to York for my fellowship, and eventually started my collaboration with Radu. And now, back then, I was doing research about the specific kind of controller that back then we called safety controllers, and I over time changed the name to supervisors, and then the process of using these supervisors in a system, in a CPS, for instance, would then be called supervision. And the focus is of course on intelligent cyber-physical systems, because their control often is critical. And nowadays CPSs are increasingly, as you all know, using AI-enabled components, or what we might call intelligent components. Today I will quickly introduce what I understand as supervision, by the concept of supervision, how one can design supervisors rigorously, soundly, and how can supervisors, once designed, be implemented and conformance tested. I'll close my talk with a note, or with some results from a recent activity on assessing sensors used in supervisory controllers, in particular sensors that use neural network components. Let me briefly summarize the collaborations over the past years. So the results you will see, or what I will be talking about, results from collaborations here at the University of Bremen, where I'm currently at, a state-funded or governmental-funded project together with Jan Peleska. And as mentioned, a great deal of the work I'm presenting is a result of a collaboration with Radu, and in particular with the CSI Cobot team, also together with the University of Sheffield, all in the context of the Assuring Autonomy International Program. And also some of the formal parts and earlier parts were coming from a collaboration with Jim Woodcock and Simon Foster during my DFG fellowship. The supervision is not a new concept. It is basically a particular technique for controlling or influencing systems. Like you can see here on the slide, there's in control engineering always a process or some kind of process that we want to control. And the component responsible for doing this is the controller. And in many industrial settings, some component of the controller is responsible for handling adversarial events. And therefore, that component, we call it the supervisor, is safety critical. The usual process of gaining an understanding about safety in such a setting is performing a hazard analysis, coming up with a hazard list, a list of hazards, and responding to each hazard with a requirement on the system, particularly on the controller. And eventually some control engineer or software engineer has to implement that requirement. And the method that we were developing is a model-based method. So it will help the engineer to perform this process more formally. And the process of developing a controller from the hazard identified, from the requirement specified, and the result of that, following the workflow that we propose, is a state machine, or more precisely said, a design space, a set of state machines from which, with an automated procedure, we select particularly useful state machine. And that state machine then is converted. It is a model of the supervisor. That state machine is converted into a piece of code that can finally be run on the actual platform. So what we did in a particular, in the CSI COVAS project, for instance, we applied a multi-objective evolutionary search and probabilistic model checking to solve the problem of automatically selecting a good or the best supervisor implementation, which fulfills some specified correctness requirements. We encoded correctness by using probabilistic constraints, and the notion of what the best controller is supposed to be was encoded using probabilistic rewards and reward structures. We used the PRISM tool and another tool developed in Radu's group, EvoChecker, using, for instance, PRISM in an evolutionary search setting. And based on the result of that evolutionary search, which we did then a conversion of the result into a state machine model, particularly a Mealy machine. And that resulted in a very nice formally based method, a workflow. There's a slide in a second which shows the workflow. I'd like to just point you to a paper that we published in the Science of Computer Programming journal, which explains all the details, nitty-gritty details about the nice work. And also, I should say that we were invited for presenting it as a journal first paper at the last year's Formal Method Symposium. That was very nice, nicely received also in the community. I should not forget part of the workflow that I'm describing to you is also implemented in a tool that I developed myself. It's called YAP, YAP Against Perils. By the way, if you have questions, please don't hesitate to interrupt me at any point in time. You might perhaps be interested in what do we actually verify of a supervisor. And there are several requirements that one can pose on a supervisor. First of all, what we definitely want to have is something called safe task finalization. So the probability of safely reaching a goal should be high, particularly beyond a certain threshold. But in the case that a task cannot be finished entirely safely, so in the case that some adverse event is occurring, the supervisor comes into play, and if the supervisor and then the supervisor, of course, has to comply with supervisory requirements. And certainly we want the supervisor to be correct in the sense that when it detects an unsafe event, it is possible in the model for the supervisor to reach, to mitigate this adverse event, finally reach a mitigated state with some probability. And when it reaches a mitigated state where the hazard is no more apparent, and then we want the supervisor to also perform further actions to bring the system back into an operational state. Those are the two bits of correctness requirements, core correctness requirements for the supervisor. Then, so there's even a notion of an accident that we allow the user to model in the stochastic model setting. And what we want to also have is that while the supervisor is working, it works in a way that no accident can happen until the safe and operational state is reached. This is also another bit checked. And of course, within this notion of correctness, we'd like to select a good controller of the residual design space. And that is, it's done, many of you might know probabilistic model checking and optimal policy synthesis. And there you can use reward structures to find an optimal policy. In our case, our optimization goals were finding a controller that uses minimal energy, that reduces certain a notion of risk also encoded in terms of reward structure. We'd like to maximize productivity by whatever that means in a particular setting. And of course, there are also some kind of well-formedness properties to be checked, because optimal synthesis is not possible in all the cases. For instance, if you have cyclic models, you can run into big troubles with Prism, for instance, because of the accumulation of rewards in cyclic structures, substructures of the transition model. So we chose to make the model acyclic. This is not a big limitation, but it makes the model larger. You have to encode the additional guards to make sure that cycles are not produced. Well, this is the core set of correctness, optimality, and well-formedness requirements that pretty much captures the requirement specification that we apply in the workflow. Speaking of the workflow, it is a multi-step workflow, every step supported by a tool, one or more tools. And I will not talk much about what you can now see on the bottom of that slide, but the idea of the workflow is that it remains within, it preserves properties. It remains within a, if you like, a pipe of correctness. Yeah. And this pipe of correctness is captured with a chain of refinements. Those of you familiar with refinement-based development, or unfamiliar with refinement-based development, I can summarize refinement as gradually narrowing a specification and ending up with an implementation. So this is a stepwise development where you step by step add details to a system while not allowing a refined development step to do more than the previous development step could do. So the workflow is quite, yeah, I would say logical. It is based on models. It starts with the user, the engineer, being required to come up with a world model, a certain notion of an environment model, and the model of the design space, which means the engineer is asked to give a specification of what the controller could possibly do. In other words, the range of actions that the synthesizer or the synthesis tool can choose from when developing the policy. Then synthesis is performed, and it results in two artifacts. It's on the one hand a reference model. It's a model that we use for testing the supervisor once it's implemented. And the second artifact coming out of supervisor synthesis is a piece of code that can actually be used, executed on the platform. And those two artifacts, they come together at the stage of testing. And in that stage, the test suite is derived. That's basically a list of test cases that allow one to perform what we call conformance tests. Now you might ask, okay, what is conformance test? The test method that we use allows, under certain assumptions, to deliver a proof of observational equivalence. It is equivalent to formal verification of the final system, of the safety of the supervisor. Yeah. As I said, under certain restrictions, and these restrictions result from the test method that we apply. It is called the W method. To be more precise, it's the what we've been using is the H method. It is a well-known method from model-based testing community, and it basically allows you to derive all the test cases that you need in order to decide whether the generated code compiled and run on the target system is observationally equivalent to a state machine model of the code. You might perhaps ask, well, if I generate both the test model and the code from the same source, then why do I need to test? What do I gain from testing? That's a valid question, but there's quite some things to gain from it. First of all, the pathway to the implementation can add further details. It can there are a few barriers or a few translations happening, down to when the code is actually a binary deployed at some platform, while the pathway to the state machine presenting the code is relatively still quite closely connected to the formal world. So there's some freedom that you gain, and if you don't leave the freedom, you still maintain the ability to perform formal verification, which is not usually possible with testing. A second advantage of that thing is that even if code and model are close together, you still keep a tight connection with the input model upon which model checking is performed. So even if the step of producing the test reference and the code are quite close together, you still can redo this process often until you find the model valid or good enough, and then you have a clear procedure to go from the model down to the platform where you actually perform and run the controller. If you like to know more about that, we have some paper on a workshop, and there is also a preprint available providing a few more details on that, but there's still some work to do, and I hope that in the next month I will be able to provide you with a long publication on this. Are there questions so far? Or might I ask into the round? This is perhaps a good point perhaps to dive a little into the testing method so you can see how it works. So with regard to testing, you should know, many of you will know, testing is the most important and the only accepted quality assurance technique in practice. So whatever you do before, whether it's formal verification or other means of quality assurance, eventually you will need to do testing. That's why in the CSI Cobot project, we did some integration testing with a digital twin. And here in Bremen, I added to this methodology another step using, as I said, the H method. And that is something that I want to briefly give you some insight into. On this slide, this slide looks a little chaotic, but essentially it's what you can see on the left top here is a graphical visualization of the policy, a decision for each of the states in the world model, from which our tool chain extracts a Mealy machine. A Mealy machine is nothing else than an I/O automaton with on each transition a pair of input-output symbols. And these symbols, they are used by the test method to derive test cases. Yeah. And these test cases are then run against an implementation of the supervisor. You can see here, for instance, a piece of C++ code that our tool generates. The structure is I think, quite reasonable. For each of the transitions in the Mealy machine, a guard function is generated from the input symbol, and an output function is created from the output symbol. So you have this triple for each of the transitions in that Mealy machine. This is quite straightforward. And also for the test tool, it will be quite the same. It'll derive input-output pairs from the same milling machine. Here you can see, for instance, a test case with two inputs. Each of the inputs can be a complex expression. And the second, well, there's three test cases actually. And when these test cases are used, for each test case, the corresponding testing tool, in our case, we use libfsm test. That's a tool developed here in Bremen, based on several variants of the H method. And it takes basically this input-output sequence, runs it, records the reactions of the system on the inputs applied, and compares it with the reference outputs listed with the test case, and concludes with a verdict, which ideally should be pass for each of the test cases. If it fails, then the whole test suite fails. Yeah, this is the usual procedure. And I can now, if you like, run a demo in the background that will perhaps finish in a few seconds while I can talk. I can continue with my talk. What the demo does is it uses the tools to capture the workflow. Sorry, there we've just seen. It performs the whole workflow that you can see on this slide. It uses Evo Checker, the case then also Prism for some parts. It uses YAP, and all that is also, by the way, available as a Docker image, should you be interested in running that and trying it out. And the result is provided in a, let's see. I hope you can read the script. Right. Let's let the tool run for a while, and in the meantime I can return to the workflow, which helps us to understand the outputs. So the workflow is pretty much represented in the directory structure you can see here. It will provide a controller, and it'll provide a test suite. Not yet. So the longest stage is taken up by the optimal policy synthesis, because evolutionary research is here applied on a quite big model. Now some outputs appear. So basically, evolutionary research needs to search through the design space and perform all the model checking that I've discussed previously. So it checks all the requirements that I mentioned for each of the possible controllers, and those can be hundreds. But when it does, it comes up with all the correct controllers, and here you can see how they are located at the Pareto front of correct controllers. And from these residual set of controllers, we pick one which by definition of Pareto front is optimal with respect to our goals. And then we can have a look into these graphs. These graphs are not so informative, but here you can see the controller generated as I hope you can see the window here. libfsm test then wraps the controller and compiles it into a test bench. And that is then used to perform the tests. And from libfsm test, you then get a big test log, which is basically a list of the test protocols and verdicts. Here you can see pass everywhere. Finally, you also get a picture of how the actual supervisor looks like. It's a simplified version of the Mealy machine that only is labeled with the action names for the sake of brevity, so you can still have some kind of user-oriented view of the Mealy machine you are using. And all this is basically done by tools which capture the whole workflow shown. Yeah, that's it. That's basically it. But now you might ask, of course, what is how do we embed the supervisor that we got from this, the piece of code, into a platform? Or more precisely, when we are using such a controller in the platform, it will always rely on sensors. In particular, if it's a safety critical component, the sensors need to be safety critical as well. They are classified, of course, because the safety critical component relying on unsafe sensor input would not be allowed to be used. This was in a train system setting. This was a motivation to perform a risk assessment of a sensor system, which you can imagine to be here at the front of the left-hand side of the supervisor component, to do a risk assessment and see what we can do to make it reliable enough for it to be used in combination with a supervisory controller. And that led us to a nice result published at the Formal Techniques in Safety Critical Systems workshop on last year's Splash conference in Portugal. The problem that we tackled was we wanted to know about the false negative rate of an object detection, of an obstacle detection sensor used in a train system to detect obstacles on a train track and reduce and forward the obstacle knowledge to a train controller. And the single most important hazard that can occur with such a sensor system is that it fails to detect an obstacle while there is one. Classical setting, but it gets interesting if you want to know about what is the accepted, or you want to know whether the actual hazard rate is below an acceptable level. In that case, it was 10 to the minus 7 for the train system we were looking at. And we chose to perform a fault tree analysis and estimate component error rates. And in order to understand the fault tree from a probabilistic point of view, we encoded the sensor system, which you can see here on the right-hand side, as a continuous time Markov chain. And then we used Prism to compute the bits and the events, basic events and intermediate events of the fault tree. Here is a diagram of the sensor system's processing stages that helped us converting the sensor system into the CTMC. And our contribution was that was a workflow from fault tree analysis of sensor systems to and the suggestion on how a parametric model checking can be used in that setting. And one of the most important insights that we gained from applying these techniques is that we don't actually need to look into the neural network-based sensor. We don't need to treat it as a white box model. We just need to make sure that its fault probability corresponds to a realistic fault probability. And there are methods by which this fault probability can be obtained. And this is exactly what we used in the basic events of our fault tree. Let me get to the fault tree just for a few minutes. There are 1,000 ways of how you can come up with a fault tree and a continuous time Markov chain model of that system. We think we managed to come up with a reasonable combination of these two artifacts. I think the most important element of the fault tree is the top element. It is the event that there is an obstacle, but it hasn't been detected. There's a few more details to that, but that essentially that's the false negative that we want to whose probability we want to estimate. Now, in order to do the estimation, we need to find an understanding on how that can possibly happen. And for that, we split the fault tree into the cases according to the architecture of the sensor system. In our case, it was a two-channel sensor system. Each of the system used a sensing component. And there we looked at the combination of a conventional camera-based sensor and a neural network-based sensor, convolutional network for object classification. And then the perception unit would further process the output and come up with a conclusion on whether or not there is an obstacle. And in the sensor system we were confronted with, there was a voting component responsible for deciding whether the output of both channels contradicts or is non-contradicting. And now the typical faults that can happen in such a system are that the channels provide contradictory results, but they are undetected. This is the first bigger fault class. Of course, the voter itself is subjected to certain kinds of faults. There can be random faults, hardware related, and there can be a voter software fault. And the third, the big kind, or here it's the fourth kind of failure, is that both channels provide the same result, but it's wrong, simultaneously wrong. We put further analysis into that, into each of these fault categories. I won't discuss all the details about that. There's a lot of technicalities in the fault tree. If you like, you're invited to read the paper. So I don't want to bore you too much with those details, but it was actually quite exciting to understand the complexity of faults and fault possibilities in such a system. And also, it was very nice to see how smoothly the model can be actually translated into a CTMC. Although, a spoiler, after all, the specific setting that we finally arrived at, it would have been sufficient to use a discrete time Markov chain, because we finally decided to exclude runtime and performance analysis of the sensor system and focus only on the fault probability propagation. Yeah, so there's a lot more to the fault tree, but what I wanted to finally, as the last, I think, result for today, discuss. Rado, may I ask how much time do I still have?
If you can aim for another 7-8 minutes, Mario.
Oh, I thank you very much. I won't need that much time. Thank you. So the most important result is on this slide, my last slide. What we did is, as I mentioned, we used parametric model checking in order to allow some uncertainty in how some basic event probabilities are estimated. And two of the basic event probabilities, particularly of strong interest, are the probabilities of the two channels. Yeah. So what is the in the fault tree, we looked at these two events, namely the faults that the perception units. So the faults of a camera-based sensor to detect an obstacle that is there, and in comparison with the fault probability of the neural network-based sensor. So there are two parameters that we allowed to be associated with uncertainty. Here we, for instance, we said that the neural network-based sensor, in that case, both sensors are allowed to have a fault probability of between 2 and 10%, actually, which I think is quite realistic for that particular train system setting. Then using these parameters results in a parametric model that can be checked. Prism allows you to smoothly run such checks, although the model needs to be small enough, otherwise there are some limits, as you might well know. And nevertheless, our model was just small enough for Prism to work smoothly. And it then leads to, okay, there should be another slide, but the result is, okay, this is basically the final result. I wanted to show you an intermediate result. It allows us to then derive the false negative probability, the probability of the top level event of the fault tree, for one sensor system used in the train, but that was still more likely than 10 to the -7, which led us to apply another widely used technique, namely multiplying the sensor units. We used a 3 out of 3 system, 3 such 2-channel units. You can see it, they are parallel composed, used in the train on different positions. In the paper, we also argue for their stochastic independence. So each of these 2-channel units have to be developed and trained independently, and then they can be used and their probability is multiplied, and we can push the fault probability of the whole system down to 10 to the minus 9, or even further, which is actually sufficient. And as you can see that from this graph, both systems can, in their instances, have fault probabilities of up to 5%, which is a realistic practical margin for a neural network-based sensor. Yeah, that's all I have to say in this regard. Before I forget it, I'd like to just quickly mention a special issue that we are currently calling for papers for. You can get more information on fmasworkshop.github.io. Now I've done my little bit of advertisement in the round. Thank you very much for listening. I'm happy to answer your questions.
Thank you very much, Mario, for a really interesting talk. It was very, very nice to hear how you continued the work and extended it so much since I last heard from you. So if there are any questions, please ask them. I can start with the questions. I suppose that this is somehow orthogonal to the work you are doing, but I think very important. Often all the planning and testing and the synthesis of this intelligent control operates as long as one can anticipate the changes, the failures that might occur in the deployed system. Can you think of extensions that might be possible for taking this to an online setting where further testing and synthesis could be done on the fly, Mario, along the lines of what you described here?
That's a very good question. I've not looked into that topic by myself. I'm aware that I think also you have done some quite interesting work in that area. Out of my guts, I have no idea on how to transfer the setting. I suppose one can, on the fly, one can run the tool chain while the system is running, and introduce some variability points in the world model at the beginning of the workflow that I've shown. So run the whole workflow during operation, but allow some variabilities here, and feed the world model with runtime information. That's perhaps an idea worthwhile pursuing.
Thank you. Any other questions? I suppose something else I wanted to ask has to do with the need to accommodate machine learning components in the systems that are being, let's say, supervised, to use your nice terminology. How could that be done, given that these components are, I suppose, unpredictable, and it is hard to figure out that they're the uncertainty they introduce into the systems. Is this a direction in which you would be interested to take the work, or are you aware of?
Yes, indeed. This is certainly one of the next logical steps in the whole workflow and the set in research. So neural network verification is an entirely different world, and I think it's orthogonal to the problem we have here. The supervisor is provided with the outputs of the neural network, and there needs to be the uncertainty of the neural network. It needs to be estimated or analyzed or identified beforehand. And then the supervisor can be designed in a way to handle each of the, or to cover the uncertainty that is coming along with the neural network. Those are two separate steps. And they definitely need to be integrated. Yeah, there's a whole lot of solutions for the first part and a whole lot of solutions for the second part. Yeah, it would be definitely exciting to see how these two worlds play together.
Mm-hmm. I'm looking at who is attending the seminar, and I am aware that some of the work done by the colleagues attending is actually related to the research you presented.
Mm-hmm.
So I suppose seeing that Mark is here, I'm aware that in some of his recent work, we together looked at ways of actually reducing uncertainty. So you are using stochastic models because the world in which a system, cyber-physical system, needs to be supervised is uncertain and affected by both, I suppose, epistemic and aleatoric uncertainty. Now, if you have constraints and optimization objectives that are too demanding and the uncertainty is too significant, I suppose the outcome of this synthesis process is going to be kind of the empty set, right? You may end up figuring out, well, that there's no way to achieve in a world quite as uncertain as you provided as input to the approach. There is no way to achieve these requirements. So in that case, and maybe that's something that could extend the process in a way when you are not pleased with the result of the synthesis, maybe it's the empty set, or it's not very maybe it's not optimizing the quantities you want. You have the ability to maybe run more testing, constrain the system in various ways to reduce the uncertainty. I see Mark is here as well if you want to add to the discussion, but very interesting.
Yeah, thanks for mentioning these aspects. That reminds me on the process of creating the model for the human-robot, for the cobot, human-robot collaboration setting, where we included sensor uncertainties, the probabilistic behavior of the human, and then even some mismatch between what the sensor provides to the controller and what the controller does, also controller faults. And all of that creates a combinatorial explosion that very quickly goes beyond what the Prism can handle easily. And there's really a big need for new abstraction techniques to focus on these very aspects of dealing with uncertainty, and then allowing further techniques to then in a second stage, for instance, to refine controllers that can on a lower level then again decide between different ways of how to handle certain situations. My lessons learned is that one model fits all is a very risky strategy. And nevertheless, for the workflow that I'm proposing, it is very helpful because it allows you to go through from the beginning to the end without leaving the rigor of formality. Being able to do conformance testing with the H method is an extremely powerful thing. Yeah, so this is, I mean, it's formal verification, and leaving that terrain is something that you need to in order to handle complex uncertainties. But you don't want to if you want to explain to the certification authority that the controller is properly tested. So there's really a lot of methodological work to do in that area.
Yeah. Is there anything you might want to add, Mark?
Hi everybody. Hi Mario. Thanks for the talk first. Not really much to add from my side. But maybe we can have a follow-up conversation at some point, Mario. Maybe I can reach out to you. I think I've got some reading to do for those papers that you mentioned here, which seem really interesting. So thanks again for the talk.
Thank you very much.
Yeah, and these are complementary parts of a bigger problem, right? Well, one is to actually synthesize something, and in a way we discussed ourselves in CSI Cobot, Mario, that perhaps having a better trained operator would allow the system to operate with higher levels of safety and efficiency. So maybe the result of the synthesis could actually be, right, in a socio-technical system, thinking of socio-technical resilience, the insight that one needs to better train their operators for their own safety.
Indeed, safety is an emergent property. Yeah. It's really emergent, and that makes it so difficult. Even if you verify a probabilistic requirement, that will depend on, as you say, some fragile assumptions about the environment. And the fragility then may be encoded with some uncertainty, but as you mentioned, Radu, the uncertainty might need to be assumed to an extent that it leads to an empty design space. Yeah. And this is really, very exciting to do some work in that area. Yeah.
Right. Well, I think it's time to thank you again, Mario, for giving this talk and sharing with us the recent research you've done. All very interesting.
Thanks for the invitation.